I think there are a few people filtering in, but for the sake of time, let's get started and hopefully they'll hurry up. This is our second to last speaker, Konstantin Genin, whose name I haven't actually asked how you pronounce. And this is work with Connor Mayo Wilson, if I'm right. Konstantin's here to talk about randomization against the tragic few.
Thanks. Maybe I'll try to stretch out the intro since people are still coming into the room. So yeah, this is working in collaboration with Connor Mayo Wilson at the University of Washington in Seattle. I thought I accidentally got into this rabbit hole because I thought the justification of randomization in RCTs must be a cut and dry thing. It must be somehow very well established, and all the theorems are clearly stated and published in all the relevant textbooks. But unless I'm terribly mistaken, it turned out to be sort of more complicated than that. So this is kind of the story of the rabbit hole that I stumbled into and am still struggling to get out of. Okay, so go. Quick. Oh yeah, I'm the leader of something called Ethics and Epistemology of Machine Learning at the University of Tübingen. I see. Okay. Right. So if you look at a textbook on clinical trials, somewhere in the beginning of the textbook, they'll say something really impressive about RCT. They'll say it's the introduction of scientific method into the process of comparing treatments. Well, basically identifying randomized controlled trials with the scientific method. If it ain't RCT, basically it ain't science, right? So what is an RCT? You probably don't need an explanation. It's an attempt to discover the relative effectiveness of a new intervention over a standard treatment or a placebo. Patients are assigned to different arms of the trial using a randomization device. It's widely considered the gold standard. It's typically necessary for FDA or EMA approval. And it raises a number of tricky ethical issues. Now, there's reason that we might want to re-examine the trade-offs that we've gotten used to making, or we think we've gotten used to making, because the pressure on the gold standard methodology is mounting from a variety of different directions. For example, over the last 20 years or so, there have been a lot of advances in causal inference from observational or only quasi-experimental designs. I'm publishing this coming from philosophers of science at Pittsburgh, or computer scientists like Judea Pearl, or computer scientists or AI ML researchers at Tübingen. That's the last book. Epidemiologists, all kinds of people are in this business now. And in some ways, the like machine learners, like people in my surroundings, are also starting kind of gunning for the RCT. They think a bandit model would be. I've talked to some machine learners, and they think bandit models would be more effective, more ethical. What is a bandit model? Well, the guiding metaphor is the one-armed bandit. The one-armed bandit is a machine in Vegas, the machine where you pull the arm and then it goes, and then maybe it spits out money, but it usually doesn't. And so the problem that you're supposed to imagine is you're faced with a bank of one-armed bandit, a bank of machines, and you have to assume, this isn't true, don't try this in Vegas, assume that one of the machines is more winning than the other one, has a higher probability of paying out. And so the problem you're faced with is what they call the problem of managing the trade-off between exploration and exploitation. You want to explore different machines to see what their propensity to pay out is, but you also want to exploit the experience that you already have acquired. And so it's a kind of way of running an adaptive. If you would try to apply this to medicine, where you imagine, the two different treatments on two arms, it's a kind of way to run an adaptive trial, and they prove various theorems about the optionality of these things. And clearly, wouldn't look. Only in the very early stages, it might look like a randomized trial, and then quickly you would start exploiting the information that you've acquired from the earlier outcomes, and it wouldn't look at all like a traditional RCT. And here are some papers claiming, no, this is better, more ethical, more efficient. So I claim, yeah, this is bandit medicine. It's kind of time to re-examine the foundations a little bit. If the randomized trial is going to withstand its challenges, we have to understand, well, what are the best justifications for the RCT, and how do they compare to the best justifications for things like bandit design? And is there some kind of dominance argument either way? Okay, so what's the trouble with randomization? The ethical problems with randomization, people are pointing them out in the 80s. It comes into prima facie conflict with therapeutic obligation. A physician should not recommend for a patient a therapy such that, given present medical knowledge, hypothesis that the particular therapy is inferior to some other therapy is more probable than the opposite hypothesis. This is Marquis in the 80s. It comes into conflict with individualized treatment. Although a patient who's been enrolled as a subject in an RCT may benefit from the therapeutic effects, the fact that the treatment cannot be entirely tailored to that patient's special needs seems to violate the physician's obligation of unqualified fidelity to his patient's health. It was also Schaefer in the 80s pointing out the seeming conflict. And the thing that emerges, well, the first idea was theoretical equipoise, meaning the investigator is in a state of genuine uncertainty regarding the comparative therapeutic merits, and then an RCT in that case is ethically permissible. Well, that was a very fragile standard, and so people proposed clinical equipoise instead, which I think is the going standard, which there exists, and may soon exist, an honest professional disagreement among expert clinicians about the treatment, and when such clinical equipoise is the case, well, then you're allowed to, violate therapeutic obligations for the good of the many. Okay. The discussion around clinical equipoise, it presupposes that there's some valuable epistemic good secured by randomization, and any trial methodology which secures this good must inevitably come into conflict with the requirements of individualized treatment. And the job of clinical ethics is, on this view, on what I'm calling the tragic view, is to reconcile clinicians to the tragic situation. Now, the clinical instincts that they have, while understandable and laudable, have the potential to obscure the true nature of clinical research, as investigators and participants alike try to convince themselves that clinical research involves nothing more than the provision of clinical care. And one way to try to address this collective and often willful confusion would be to identify a justification for exposing research participants to net risks for the benefit of others. So the poor clinicians, they think that they can be scientists and doctors at the same time. These things are just in a kind of irreconcilable tension, and the job of the ethicist is to furnish them with arguments that it's acceptable to forget about their clinical obligations in the context of a trial because they're being assigned. But is the tragic view right? What is this valuable epistemic good secured by randomization? And is there really no methodology that reconciles this good with the ethical requirements of individualized treatment? And could randomization actually be that methodology that we already live in the good world where these things are reconciled? Yeah, that's my central question. And of course, randomization has come into criticism, not even on ethical grounds, but on purely epistemic ones. For example, Bayesians cannot rationally reconstruct randomization. Or I would say, we should say this. If you're a Bayesian and you're designing an experiment and you're looking at all the deterministic ways of assigning patients to treatment, and well, you're a Bayesian and you're faced with a decision problem, so you maximize expected utility. And only in the situation in which you think two of the designs have equal expected utility would you randomize between them, right? So only if the Bayesian believes that all of the designs are equally good, yield equal expected utility, then she would be permitted to randomize between them, but she would not be required to, right? Because, well, If all the things are equally good, it's okay to randomize between them, but it's also okay to just pick one, right? Just pick a deterministic design. So Bayesians just cannot make sense of this thing. What's even stranger is that the frequentist theory of optimal design of experiments also doesn't endorse randomization. That's when I learned that, that's when I started to get nervous. Because it's just like, well, what's the answer? And of course, philosophers of science have criticized the coherence of randomization. Okay, what is the best frequentist justification for randomization? If there's no Bayesian one, it's got to be a frequentist one. So what is it? Well, okay, I'll tell you what they taught me in grad school. Remco probably remember. You can check if I'm reporting this honestly. Okay, so we draw this causal situation. We have a treatment. It's let's say for the sake of the simplicity, it's binary, and we have an effect that's binary. We have some measured covariates, which might be common causal with the treatment and the outcome. And we have some unmeasured common causes, which might also be some unmeasured things, which might also be common causes of both of them. And we might have some randomizing device, which is only a cause. It's an exogenous source of randomness, which is a cause of treatment and nothing else. Our goal is to estimate the average treatment effect. What's the average treatment effect? Well, if you prefer the Pearl-Do notation, look at the first line, but I'll pronounce the potential outcome stuff. There's a random variable there are two random variables for every patient in our trial. What would happen to them if you were to treat them, and what would happen to them if they were assigned to control. Unfortunately, you only ever observed one of those, but it makes perfect sense mathematically to look at the probability that they have a good outcome under treatment, subtract that from the probability that they have a good outcome under the control, and then average that over all the people in your study. And that's the average treatment effect. I mean, you can't compute it because, well, apart from the usual statistical problems, you only observe the realization of one of these potential outcomes at any time, at most one, if you. Okay, so the trouble with observational studies is that if there is an unobserved common cause of the treatment and the effect, it's easy to come up with examples in which the average treatment effect is not identified. What does not identified mean? That means that you can write down two different causal situations, and that's very sad, by the way. You can write down two different causal situations where the treatment effect is different that produce precisely the same statistical distributions over the things you can observe. So the point of this, and I give you a little recipe for coming up with this in linear models. The point of this is there's nothing you can do statistically to tell apart these two situations because the distribution over things you can observe is precisely the same in both cases. And so that's the worst. You know. And the point of randomization here comes to the rescue. It breaks edges into the treatment so that there's now no longer any edges into T, no longer any arrows into T, so that any association between the treatment and the effect is due to the causal effect of the treatment and not on shared common causes. And you can prove that it ensures that the average treatment effect is identified and it's equal to, well, you take the average outcome in the treated population and subtract the average outcome in the untreated population. And that gives you an unbiased estimate of the average treatment effect, which is terrific. But what does that mean? Like we call unbiased, it's like the joke about the statistician. What does it mean to be an unbiased archer? An unbiased archer is someone who is there Trump? But so if you like consistently miss by 6 feet on the left and consistently miss by 6 feet on the right, you are unbiased because on average you hit the bullseye. That's all that unbiased means, is that in expectation, your estimate is equal to the true ATE. It doesn't mean that it's close. It just means that on average it's but even though unbiased estimates are rather unexciting things. They're not something to get too excited about. I mean, it's nice, but it's not so great. People say in ideal randomized experiment association is causal because you can just do this thing like falling off a log, and just take the average outcome in the treated, the average outcome in the untreated, that gives you nothing. So it's like falling off a log, statistically speaking, and that means in this situation, association is causal. Okay, that's good. But is randomization the only way to render the average treatment effect identified and construct unbiased estimates? What this shows is that it's sufficient. The question is it necessary? And the answer is no. Unfortunately not. Maybe, I don't know, fortunate or unfortunate. Unfortunately for me, who has to come up with the reason that we should do this. And there are many ways of constructing unbiased estimates that don't, of the average treatment effect, that don't look like traditional random trials. Now, I'm going to suggest some ways, and I don't want you to misinterpret me. I don't think you should do these things. I think these things are crazy. And the fact that these crazy things still give you unbiased estimates shows you how weak this unbiased estimate thing is. It's a kind of reductio of the unbiased estimate standard of goodness that it picks out that the methodologies that give you unbiased estimates are exactly the good methodology. So the point is to suggest the methodologies, which are kind of nutty, but still give you unbiased estimates. For example, the statisticians among you might know what, the economists among you might know what instrumental variable is. An instrumental variable is roughly an exogenous cause of the treatment. Like the classical example is if you're interested in the effect of being drafted in Central Vietnam on your lifetime income or your salary or your whatever, then your draft number, which was the result of a random lottery, is an instrument for whether you were sent to Vietnam, because it's just a random thing which is a cause of being drafted into Vietnam. It's not a deterministic cause in the sense that if you had a low draft number, that doesn't mean that you have to go. There were exemptions and things like that if you had a family or if you went to college or whatever. But it didn't completely control what happened, but it was a promoter, an exogenous promoter of being sent to Vietnam. And if you have one of these things, these kinds of instrumental variables, what is an example? Well, suppose physicians assign patients to treatment according to their therapeutic judgment, and they only consult a randomizing device when they're in equipoise. So they always use their judgment, and they only when they're on the fence do they consult the randomizing device. Then the randomizing device is an instrument. So here's a theorem from some famous economists. When an instrumental variable satisfies a monotonicity condition, which I won't get into because it's quite weak and not so interesting, then the ATE is identified, and there is an unbiased estimator of the ATE. Great, so we just let physicians do whatever they feel is right, except when they're on the fence, then they put the coin in, and we get an unbiased estimate of the ATE. But everyone knows that you're not supposed to do that. I mean, that's not a virtuous design for a million different reasons, right? Well, this is an ironic smiley. Okay, Pearl proves the backdoor adjustment criteria. If you have a set of variables, if basically you know all of the common causes of the treatment and the outcome, then that set of variables satisfies the backdoor criterion, and if you have it, then it's possible to construct an unbiased estimate of the causal effect. Basically, if you have observed all the common causes, there's no unobserved common causes. Okay, but when does that happen, right? You're saying, well, what I'm saying is, if you're in a position to run a randomized trial, you're also in a position to run a almost deterministic trial, where assignment is made deterministically on the basis of things that you wrote down and observed, so that all of the common causes and all the causes of assignment and treatment are observed, but all the common causes are also observed. So physicians make assignments of treatment only on the basis of observed covariates. Then you have this thing which satisfies the backdoor criteria. You have to randomize a tiny bit to satisfy a technical thing called positivity. But you can essentially, as long as you make your assignment decisions on the basis of things that you have observed, satisfy the backdoor criteria and get an unbiased estimate. Again, nobody would do this. It's crazy. It's just to show that getting unbiased estimates of average treatment effects is relatively cheap and easy. And you can do it in ways consistent with giving physicians almost total discretion, almost total. You need to inject some small amount of randomness, an arbitrary small. There's more ways. Cutoff design. You know, if you assign at intake people with substance disorder a severity score, low, medium, high, you send all of the ones who are high to be inpatients. All the ones that are low, you send them home as outpatients. The ones in the middle, you randomize them. Then you can do ridge regression and get an unbiased estimate of the AT because you inserted a little bit of randomness. Okay. I mean, the point of this, which at this point probably you're getting a little sick of it, is that it's easy to come up with experimental designs that can be unbiased. The problem is probably the efficiency of the designs. So, for example, Sen criticizes the cutoff designs on grounds of efficiency, and he generates this kind of experimental thing. Efficiency is the variance of the estimate, right? So maybe the point was just, okay, it's not that randomized control trials are the only way of getting unbiased estimates. Maybe they're the way of getting the lowest variance unbiased. What does variance mean? Well, it's not that I hit the bullseye on average, even though every time I hit it 6 feet to the left and 6 feet to the right, but I need things to cluster near the bullseye. That's low variance and unbiased. But okay, the point so far is neither guaranteeing that the AT is identified, nor that there exists an unbiased estimator of the AT is sufficient to justify randomization. Other designs get the same goods and are less hostile to individualized treatment. The usual story establishes the superiority of experimental designs over observational designs. It doesn't establish the superiority of any particular randomized design over other experimental designs. It's a story, you know, breaking edges into treatment. It's a story for doing experiments, because in experiments, you decide who gets which treatment, not nature. That's the problem with observational studies. Nature decides it, and you don't know what criteria nature is using to make a decision. But when you're doing experiments, you decide what the cause of the treatment is. So the usual story that the usual justification that I received in grad school was a justification of doing experiments that was masquerading the justification for a particular kind of experiment, a randomized trial. So, if there is a frequentist argument justifying randomization over other methods, it can't be framed in terms of identifiability or unbiasedness of estimates. It's got to be about efficiency, because it's the only thing I can think of that's left. In other words, the variance of the estimate. Now, are there such arguments? There are definitely no dominance arguments. Like, it's not always going to give you a lower variance estimate. And for example, if you know that if the outcome is just like, will the patient survive in the next 6 months, 0, 1. If you know that under no treatment, everyone dies, then the way to get the lowest variance estimate of the treatment effect is to assign everyone to treatment. Because you basically just want to estimate the mean of a random variable. The best way to estimate the mean of a random variable is to get the biggest sample size. That's the law of some large numbers, I suppose. And okay, or the central limit theorem. So if you know that everyone will die if they don't get treatment, and you want to just minimize, I'm not doing some software who cares about ethics. I just want to minimize the variance of the estimate. Well, then I have to assign everyone to treatment, because bigger samples means lower variance. That's just basic 101 stuff. So this is like, you know, this is why you wouldn't really do an RCT test character, because you know what the effect, the potential the expected outcome under control is. Everyone got it. So the only question is estimating the average outcome under treatment, which is the parachute. And so if you wanted to minimize the variance of your estimate of the effectiveness of parachute, you should give everyone each other. There might be minimax arguments in other cases, worst cases. So we've seen there's no frequentist dominant case. There's no expected case argument, because if we do Bayesian, expected cases Bayesian, we know that doesn't work. And there's no frequentist dominant argument, but there might be a frequentist worst case. So here we have to visit the theory of the optimal design experiment, which was invented by this woman, Konstantin Smith, a Danish statistician credited with the creation of the field of optimal design. Pearson considered her to be one of his most brilliant, what does it say? How do you make it go away? Brilliant mathematical statistician. And apparently it led to a controversial dialogue between Pearson and Fisher, and led to Fisher's introduction of sufficient statistics. So apparently her dissertation led to a fallout between Fisher and Pearson. I don't really know the details, but it sounds interesting for someone to explain to me if they know. Okay, now what? Okay, so how does this work? Quickly, in a nutshell, we have n experimental units. For example, plots of land on our agricultural research statement for patients in a trial. We have two treatments, for example, varieties of wheat or eating drugs. We write the outcome for the ith unit under treatment T in this way: y sub I sup T. And we're interested again in the average treatment effect, but we only observe a realization of exactly one of those things. Okay, so a design is just an assignment of units to treatment. We need a function sending everyone to one of two things. And now let D be the set of all those assignments. Let Y sub F be the observations arising from a particular design F. And then we have an unbiased estimator that takes the observations arising, which is usually the difference of means. And we have some loss, usually the mean squared error, that determines how good, how far off you are, how far off your estimate is. And the goal is to pick the design that minimizes the expected loss. Quite straightforward. You just want the design that minimizes the expected loss. But here's the thing. The theory of optimal designs considers only deterministic designs. These are all deterministic functions F. We're just searching over deterministic assignments. It considers only deterministic design. Doesn't consider random. You just jump up and down about this a little bit. The theory of the optimal design of experiments, the frequentist theory of the optimal design of experiments, only considers deterministic design, not randomized design. If you don't believe me, here's a paper from the Journal of the American Statistical Association from 2022, which is just last year, which says the following. Okay, the above property, meaning the property that the deterministic minimizer has, gives a strong argument in favor of the use of this deterministic minimizer. But in fact, in both game theory and statistical decision theory, it's widely recognized that a minimax deterministic decision is often outperformed by a randomized decision strategy. What are they saying here? They're basically saying that if you're playing rock, paper, scissors, then the strategy which minimizes the worst case loss is randomizing between rock, paper, and scissors. And each of the deterministic strategies, like always playing rock, always playing scissors, has a worst case loss if you lose $1. But the worst case expected loss of the randomization strategy is 0. You get nothing. Because in the worst case, whatever strategy your opponent is playing, the expected outcome of your randomization strategy is, well, 1/3 of the time you lose, 1/3 of the time you win, and 1/3 of the time you so 0. So, and they continue. Since design selection can be viewed as a decision problem, or alternatively, a game pitting the statistician against nature, it stands to reason that random decision strategies should also be beneficial for experimental design. Nonetheless, aside from a few minimax analyses of Fisherian randomization, so-and-so, so-and-so, and so-and-so, the topic of minimax random strategies for design selection appears almost totally unexplored in the literature. Okay, this is last year. This is people who know about design experiments, and they're saying that randomized designs are almost totally unexplored in the literature. I mean, what is going on? And why is this happening to me? Like, why me? I have to find it. So, okay, there's a series of somewhat neglected papers, and they develop minimax risk arguments for randomization. Here's roughly how those things work. You write down this additive equation. Everyone's potential outcome under treatment is there a fixed effect, the effect of the treatment, plus their individual patient effect, that's like the Casey effect, the me effect, and plus some independent, identically distributed mean zero noise. Now, G is just an assignment of patient effects to individuals, just ways that people can contribute to the outcome, all the ways that people can contribute to the outcome. And let G be all the ways that they can contribute to the outcome consistent with your background knowledge. So you might think, well, younger, healthier people, they're more likely to survive, older ones, blah, blah, blah. And now we have a collection of permutations over these things. These permutations, if like Remco is the first one in the vector, the first patient, I'm the second one. If there's a permutation commuting me and Remco, that means anything that you think is a possible patient effect for Remco is a possible patient effect for Casey and vice versa. So we are from a clinical perspective equivalent. We are like clinically equivalent for all the investigators know. And now let R be the set of randomized design, random variables taking values in D. Theorem. Suppose that pi is the set of all permutations, meaning all the patients are equivalent from your perspective. You can't tell the difference between any of them. Then the balanced, fully randomized design minimizes the maximum loss of the estimate of the treatment effect over all possible values of G. Okay, that's nice, but note that the canonical randomized design minimizes the worst case estimate, the worst case loss of the estimate of the treatment effect. So the fully randomized design has the best worst case efficiency. What's wrong with that? Aren't we done? Well, note that we assumed that the set of permutations is all of the permutations. All of the patients are from your perspective equivalent. And if they are all from your perspective equivalent, then you can do balanced randomization, and that's optimal. But of course, if you assume that all the patients are from your perspective equivalent, there could not have been an ethical dilemma in the first place, right? It's like, you know, if I have 10 children, and from my perspective, the children are all equally deserving, and I have 5 pieces of candy, then the ethical, just way of distributing the 5 pieces of candy is random. Well, if they really, it doesn't matter if they agree. Well, that's the right thing to do. They're all equally deserving. It's arbitrary which ones they give it to, so you know, randomize. There's nothing ethically wrong with doing that. They might not like it, but I haven't done anything wrong. I've never done anything wrong. Okay, so notice this theorem has no interesting ethical implications whatsoever. How much time do I have left? Okay, good. Okay, now a speed run through an attempt to maybe give a minimax justification for some kind of randomization. So, okay, a state, that's just a big matrix of random variables, 2 for each patient, their potential outcome under control and treatment. Now let big S be the set of all such states that you consider possible. If you know all of this stuff, you know everything about the average treatment effect, everything. Let pi be that big set of permutations telling you who is equivalent. Okay, our first assumption, if G is a state and pi, I think maybe I did the stuff wrong, I'm sorry. If G is a possible state and pi is in this big set of permutations that capture who you think is equivalent, then pi G is in pi. That's just what it means for you to consider this thing to be possible. Yeah. In other words, the permutation group partitions people into clinically equivalent strata, for example, like the people who are under 45 and severely ill, over 45 and severely ill, or all the ways of partitioning people into those four things. Okay, an assignment vector, well, an assignment vector just assigns every patient to some treatment. It's just a vector of zeros and ones. And it determines the outcome by multiplying, basically for each person, you just multiply, did they get the treatment, and then you pick the realization of the potential outcome of the treatment, and or did they get the control, then you pick the realization on the control. There's nothing going on here, nothing special. An estimator is a function mapping pairs of assignment vectors and outcomes to some number. So if I know what the assignment, I know who got the treatment, who got the control, then I can, the usual estimator takes the people who got the treatment, looks at their outcome, averages them, takes the people who got the control, averages them, and subtracts. But an estimator doesn't have to be that kind of thing, even though that's the usual kind of thing. An estimator can just count the number of adverse outcomes. That can be the clinical result. That's not normal, but if you didn't care at all about guessing the ATE and all you cared about was how many people are healthy, study, then the estimator can just output the number of people who died or didn't die, whatever. Okay, there we have an assumption that the estimate, the result of the estimate depends only on the set of treatment outcome pairs in each group, but forgets within group identity. So it only depends on in each group that in each equivalence class, you count, you know the set of treatment outcome pairs, but you don't know who got it. So if Remco and I are in the same equivalent class, then it doesn't matter which the estimate wouldn't change if Remco got it or not, because we're equivalent. It doesn't matter. Now we have a loss function, which takes states and estimates to a real valued loss. For example, if it's the average treatment effect, it's a function of the state because you need to take the expected, the average treatment effect, that's a function of the state. I mean, sorry, yeah, the average treatment effect, and then you subtract the estimate, and then you square it, that gives you the usual squared error loss. Or that's the usual epistemic loss, the squared error loss. Or it can be a clinical loss, just the total number of people who died. It doesn't matter. That's also a loss function. Okay, so the last assumption is that if I permute the state, the loss doesn't change. Notice if you permute the state, the average treatment effect doesn't change. It doesn't matter when we take the average of everything in the first column and everything in the second column. It doesn't matter what order the rows are in. If you reorder the rows and take the averages of the column, nothing changes. Another way of satisfying this is just by having your loss function ignore the first parameter. So if your loss function doesn't care at all about average treatment effect, it only cares how many people died, then you can just, the loss L of SD is just D. And so of course it satisfies this other thing because it's just ignoring the first parameter. Okay. Or almost done. You can almost state the theorem. Okay, so if you have some assignment, let's just think about it. Now, U is just a way of picking a permutation from your permutation group at random, each one with equal probability, and then hitting the assignment with that. So, for example, if A is this assignment that in the first group, the first two patients get the treatment, the next two get control, and the second group, the first two patients get the treatment, the second get control. Then U, if I hit that thing with U, it becomes a random assignment that randomizes between all designs where precisely two patients in the plot get the treatment. So it only takes the treatment numbers inside the block to randomize uniformly. Okay, theorem. This is inspired, but not. This is inspired by this paper by in econometrician. Suppose our assumptions hold, then for any assignment, even a random, the worst case loss of hitting that assignment with the uniform randomization is no worse than the worst case loss of the assignment itself. So if I pick any deterministic assignment, in the worst case, well, just hitting that with the randomizer is no worse than the worst case of any determinant. So you can never do worse by randomizing, but notice that you're only randomizing in blocks. We only randomize between equivalent, not between non-equivalent. So a worst case analysis of in a worst case analysis, randomization never hurts. But look, this holds independently of the loss function that we picked. It's true even for the therapeutic loss function. That's why I want to do a fewest number of people to die. Randomization also won't hurt if I randomize among equivalent people. Randomization also gives me doesn't hurt in the worst case just the clinical loss. So what does that mean? There's no trade-off. If you consistently do a worst case analysis, then randomization is no worse. If all I cared about is how many people are healthy, and I do a worst case analysis, then I can't do worse by randomization, and I might do better. What that means is that there's no trade-off between the clinical outcome and the epistemic. The real problem is finding the optimal number of people in each group to assign to treatment and control, not randomization. It's like the kid and the children, the children and the candy. If somebody tells you, look, I'm going to give you 5 pieces of coal and 5 pieces of candy, and you have to distribute this coal and this candy among equally deserving children, then the thing to do is to randomize. But the question, how much coal and how much candy should have been distributed in the first place? That was the ethical question, right? Why do I have to give any of them coal? Why shouldn't they all get candy? That's ethics, not if I have to give them all one of these 2 things. What's the fair way of doing it? Randomizing is fine. So there may indeed be ethical trade-offs between individualized treatment and optimal treatment numbers, but randomization doesn't have anything to do with it. Randomization makes it better as far as I can go. Okay. Takeaways. Under an average case analysis, randomization is at best epistemically permissible and never epistemically necessary. Under a worst case analysis, block randomization is sometimes epistemically necessary, but it is not in conflict with requirements of individualized treatment. And optimal treatment numbers may represent a trade-off between the epistemic and the ethical. And last takeaway, the tragic view is not a theorem. There's surprisingly a lot to learn about randomization. If I'm wrong, by the way, and there really is some trade-off between design and efficiency of individualized treatment, then a trade-off is to be managed. When there's a trade-off, you have to manage it scientifically. You don't just say, oh, there's a trade-off, therefore we have to pick one pole before randomization. That doesn't make any sense. If there really is a trade-off, then what you have to do is find the sweet spot, not just say, oh, well, forget about it. But that's if I'm wrong. Hopefully I'm wrong. Thank you.
Okay, great. Questions? Arjun's hand was up first, so we're going to go there, and then I might put myself in the queue.
Thank you. My understanding of the ethical problem is treating everybody as equivalent, right? That seems to be the problem because they're clearly not equivalent. So we're assuming that they're equivalent with respect to the likely response to treatment. But again, you have to take a view on that.
Mm-hmm.
And it seems that that requires a kind of theoretical equipoise, because it's only one person giving the treatment, that is highly implausible that any clinician would think that this like 68-year-old woman and this 95-year-old woman who are both being randomized into this chemotherapy
Mm-hmm.
are equivalent. Like, we're not going to think that.
Yeah, thank you. Okay, so I stand here. The amazing thing is that all the treatments are all the theorems are about, blocking what you can and randomizing what you can. So the theorem only says that you should randomize among people who you consider, from your perspective, clinically equivalent. And will there ever be two people that are really clinically equivalent? I don't know. I mean, maybe not. But if there were such people, it would be okay to randomize among them. So I think you're right. I mean, it's rare, but the math is picking up on it. It's not like the math is ignoring it. It's noticing it. The result is only about randomizing among equivalent people. They could be equivalent from a clinical perspective, but also I think you can even make them add in the ethical angle to say these people are ethically equivalent. I don't know if you should.
I'm actually going to put myself in here because it's a bit of a follow-up. So, I mean, there's a question about whether they're going to be ethically equivalent once you include their values as well, which will complicate this further. But I'm kind of thinking, so what my understanding of equipoise, and so I think my general question is about why you're framing this in terms of equipoise, because my understanding of equipoise is for any individual patient and the positive duties that doctors have towards those patients and the kind of what we would say is a right and also a patient preference to have the best treatment possible. There's just this fundamental tension when you're thinking about putting someone in a trial where there might be a little bit of evidence or some kind of degree of belief that one side of the trial, one intervention is just better than the other. And I don't really understand how this is going to manage that concern, because the question, so the analogy wouldn't be, and I'm clearly missing something here, because the analogy isn't coal and candy, and it's fair to randomize because they're all equivalent people. It should be something more like two types of candy. They all look the exact same. Some of them happen to taste better than the others. And then you randomize it, and whoever gets the ones that taste better, well, that's fine because you have no way of deciphering. So what am I missing?
Yeah, I mean, I think the intuition that their intention is an average case intuition, and in the kind of Bayesian, if you're being a Bayesian about it, you just shouldn't randomize. So they are intention from an average case perspective, and from an average case perspective, you certainly never have to randomize, and you probably never would. But okay, if I'm going to say, well, there's got to be something to our gold standard methodology. There's got to be something to be said for it. I'm going to say, okay, well, what's the frequency for it? And then you get down to this worst case perspective, and in the worst case perspective, randomization neither hurts epistemically nor clinically. So if you can consistently take a worst case perspective, which we never do as humans, we will never do it. That's why we don't have this intuition. It's completely unintuitive because we don't read it, right? But if somehow we consistently did, we would realize that there's actually no.
Okay, it doesn't seem to help ethically, but I can talk to you later about this.
Konstantin, thanks. That was so interesting. I got a specific question, but I've also got, I want to understand the general thrust of the talk. So as I understood it, we started off with the tension between randomizing, doing RCT, and the ethics. And the ethics says you can only do an RCT if you're kind of super equipoised, you're kind of neutral between the two treatments, and what's more, that holds across all the patients, right? And then you said, but why are we worrying about randomized trials? Because they're observational or quasi-experimental procedures that will give us the answer we want, average treatment effects. So we had that on. And then you went across to the randomization and you said, well, in the case where you are super equipoised, randomizing is fine. So have I missed something? Because I mean, it's all interesting, but I'm not getting a continuous kind of narrative. So that was a question about the thrust of the talk. And then just a few times you started saying that you wouldn't be interested in randomizing if you're Bayesian, and that seems to me all wrong. And I mean, I know Peter Urbach says that it just seems to me a terrible confusion. I mean, randomizing isn't to do with statistical inference, it's to do with telling whether your population correlation that you got to by statistical inference is spurious or causal. And both Bayesians and frequentists have that same issue. Once they've got the population correlations, what are we going to make of it causally?
Yeah.
Okay.
Okay. So just the big picture is, okay, if I guess I should address from the last question. If I want to understand the efficacy of the treatment, then, and I'm a Bayesian, then I want the design which is most informative. And I know that if I randomize, I might get an uninformative design. Like it might happen by chance that all the healthy people are assigned to treatment, and all the sick people are assigned to control. And so if I'm a Bayesian, I say, why would I randomize between designs which have where this lottery has a positive probability of a design that I would never consider informative? And so I should just, look among the designs, consider which one I would find subjectively most informative and pick that one. Okay, but that's Bayesian thing. Okay, but what we really want, let's say we're not like that. We're frequentist and we want unbiased estimates of the average treatment. Well, the first point of the talk is it's easy to get unbiased estimates of the average treatment. In fact, there are many designs that do that, which are totally nuts and no idea. So it can't just be unbiased, it must be efficiency, like minimum variance. And so if it's minimum variance, well, it doesn't always mean minimum. It's just maybe sometimes it's the worst case minimizing variance. And so now I'm looking for an argument that it is in randomizing, in fact, minimizes the variance of an unbiased estimate in the worst case. And are there such arguments? Kind of. But when we really follow through that whole line of reasoning, what we get to is that if you consistently take a worst case perspective, you learn that there's no trade-off between the epistemic and the ethical. It's just that we don't really consistently take a worst case. We usually our wet bear, I think, wants us to be Bayesian. And that's why we feel very strongly that there's a trade-off. Now, I don't know. You can consider. I'm not a super Bayesian theorist or anything. Maybe there is some way that Bayesian could. Connor thinks that Bayesian could agree to randomize essentially through a process of negotiation between them because they can't agree on what would be the most informative design. So randomization is just like a kind of, like, oh, you want this is your I have this prior, you have that prior, you think this is right, I think, but let's split the difference in random. But that takes a more subtle formal epistemology for me.
Good. Okay, thank you. I'm being a really bad chair and just randomly going to people. So sorry, everyone.
Thanks, Casey. I had a question about the first minimax theorem. I think I just didn't really understand what it was saying.
Which one?
The first minimax theorem, the one that's supposed to show that if everyone's equivalent, then randomization is good. How does that deal with the case which you had shown just before, where it's clear that giving half of the people not the treatment is definitely bad?
How does it deal with the case?
Like the parachute case. Like why is it like in the parachute case you don't want to randomize, as you said, but that I'm trying to follow how that fits under this case, under this theorem.
That's a good question. I have a feeling like, yeah, there's a transparent. But I don't know. I haven't revisited the theorem from you since I thought about the parachute case. And these papers from the 80s, like when you finally read them, they're not always totally above board. So it might just be a suppressed premise, or it might be
it could be that has to do with what we're taking in this case.
I think it's going to fall out of the fact that Wu imposes a kind of silly model where there can't be any heterogeneity in the patient population, but like if you write down this model, the same treatment is best for everyone. So it's kind of a silly OTOs model in the first place. And then, but what follows from that? Yeah, I'm sorry, I can't figure it out. Just on the fly, I have to think about it.
It's really interesting. I guess having come from a discipline where we largely do sort of whole population clinical studies, I have taken part in all of those trial designs, which have included randomizations, and they've all been used in different circumstances in what seems to me a totally appropriate way, an ethical way. And indeed, this sort of parachute study would be the standard way we would approach a situation where there's no expectation of survival, is to give everyone the intervention. And similarly, in most of those cases, if we felt that there was a strong clinical decision not to randomize somebody, you don't randomize. That's so I'm a little bit confused by some of the ethical questions that are being raised around this.
It's a parachute is right.
Yeah.
Parachute is right, but not considering what other people want.
Well, I mean, the general thing is based on the clinical evidence. If we know that one treatment is better, then we shouldn't be randomized. But generally we don't. It's a recognition that we don't. But it's the same. We don't know anything about that patient that's going to make it clear that one better treatment. Well, if we know something that we believe or for a reason believe that it's going to be better for that patient to receive treatment. Sometimes it's unavailable. Sometimes we're unable to do experimental treatments except in that's a slightly different issue.
So wait, is it that everyone the designs that I said no one would do, people do all the time? That's what I did wrong. Yeah. Okay. Yes, that's true. But I would say maybe I exaggerated that a trialist wouldn't think. I think hardcore trialists wouldn't say that these are virtuous designs, but they still give you unbiased evidence, so they're okay.
Yeah. I mean, this is pragmatic. It can be really ethical to do one-to-one randomization in some groups, and then another group you know that they pour out from the standard treatment.
What I was looking for is, suppose I didn't care about ethics at all. I only cared about the average treatment effect. I only cared about really nailing this thing. Would I then do the standard balanced trial? And I couldn't find an argument for it. That's what I'm looking for, and I can't find an argument.
One question here.
Thanks. This is really interesting. I think about this stuff in a very non-rigorous way, and this is really nicely rigorous, but I just wanted to try out. Okay, so the virtue of randomization I see is not to do with the known confounders, it's to do with the unknown confounders. And if we've got unknown confounders, then we'll get this unbiased assessment of the randomized treatment effect, but that won't help unless you repeat your study lots of times, and if you've got lots and lots of studies, then eventually you might get a kind of good answer which helps you work out what the actual efficacy is. And so it seems sort of obvious, and this is where this is me being vague and hand wavy, but it seems sort of obvious, right? That if you randomize only 2 patients, then your convergence to the answer will be much, much slower than if you randomize all of your patients. And so that seems to me like a pretty good argument in favor of the kind of randomization. But then you were asking this other kind of question about if we've got kind of known confounders, then we could say sort of stratify on the basis of known confounders and then randomize within that block, and that helps with the unknown confounders. And then you had this assumption that that will involve, far too much stratification, and it's not clear to me that the ethical considerations and the epistemic considerations run together. So it might well be the case that we know of no confounders that relevantly distinguish between 2 potential people, but we might nonetheless have ethical considerations which tell us that we should treat one rather than the other. I mean, one might be an engineer who can save lots of people's lives, and one might be a layabout, for example. I mean, not that that's a good ethical consideration, but just, exactly. But like the ethical and epistemic considerations aren't obviously going to run together in the way that I thought that you were assuming.
Yeah, I mean, okay, the first part of the question I really liked, I could have skipped a lot of the slides, dramatically illustrated the point, but I'm like, throwing away most of the data. That will be, maybe that's a thing, really no one would do it. And you have to do one line. So, thanks for bringing that example, it's really nice, I could have saved a lot of time with it. But your point that, yeah, so Connor has suggested that it's not enough to consider the permutations, the clinical people who are clinically, but rather, Connor has conditions that are much better, much more solid. You have to consider people, maybe you have to consider people who can't, maybe you can't just have a real valid loss because certain kinds of loss are inevitable. So it can't be, maybe the loss has an epistemic and an component, and so then you want to minimize some of this. You can get more sophisticated and try to prove the appearance, which is better. But it's not. Another. I haven't looked at that. It often involves a lot of confusing decisions. You have two components go wrong. What is it? Should it be like the graphic? Should the ethical always override the you trade them? And then you get into a lot of like finicky and very first. So I don't know. I just prefer that. Okay, suppose I just went full epistemic, or suppose I went full ethical, well, I get the same recommendation either way. And so randomization, there can't be trade-off. So that's, but I mean, the stuff I'm not.
This has been really interesting. Thank you so much. I think just quickly, because we have only 5 minutes technically in the break, let's take an extra 5 minutes, and David, you start your talk 5 minutes late and then we finish 5 minutes late. I hope that's okay. Thank you very much, Casey.